Hi everyone, and welcome to our next video lecture. So today I'm actually going to walk us through making sort of a cheat sheet in Excel, which is basically it's going to be a setup so that whenever you interact with any of these distributions we've been talking about, such as the negative binomial, the Poisson, regular binomial, geometric, and then the normal distribution as well, instead of doing all of the hardcore thinking that we've been doing, if you put in the work to set up this cheat sheet I'm about to show you how to do, then you'll be able to just plug things into Excel and get probabilities really quickly. So let me share my screen. I believe you all should be able to see this. And let's do it. So I'm gonna call this one, let's start with the negative binomial, which I hope we've done by now. If we haven't, I guess you can still make this, but we'll probably get to it in a day or so if I didn't get to it during class today. So there are a number of inputs for the negative binomial distribution. There is, let's see exactly how I wrote it out. There's P, the probability of success. There's R, the number of successes we want to see. And then there's K, which is our input, the number of trials we have to go through before we see that number of successes. Right? And what sort of things, so these are our three inputs, what sort of things do we want to be able to calculate? We want to be able to calculate the probability that X is equal to K. We want to be able to calculate the cumulative probability that X is less than or equal to K. What else might be nice? We might want to know the expected value. We might want to know the variance. So these are all of the different things that we have. Note that these three things, the probability, the number of successes, and the input K, are the three things that are going to change. So when you come up with a new negative binomial distribution problem, you should read the problem and try to figure out what these three things are. So I'm actually going to highlight these in yellow to signify that these are inputs, right? These other things are consequences. Once we know the three inputs, the P, the R, and the K, we can calculate these three values. And I'm going to show you how to do that in Excel. So for the probability of X equals K, we want to use this function called neg_binom, so negative binomial, .dist. So just like the norm.s.dist, now we have neg_binom.dist. And what we want to put in is, for the first part, we want, it takes in K minus R. For the second thing, it takes in R. For the third thing, it takes in probability. And then since we want the probability at instead of cumulative probability, the fourth input is just 0. So I'm gonna leave this up for a second. Maybe I'll even zoom in a little bit so you can all see it a little bit better. So the first parameter of this function is actually our K, our total number of trials, minus R, our number of successes. So Excel requires it to be done in this way. The second input is the number of successes we're looking for, which is R. The third input is the probability of success, which in this case is P, which we're going to input in B2 in a second. And then since it's not cumulative, but the probability at a point, we put 0 for the last thing. So it doesn't have anything because we haven't put in any numbers. So maybe to see that it's working, let's put in the numbers that we did for our in-class example. So I believe we wanted to know if I took 10 students, what's the probability that my first generation student happened on my 10th draw, and the probability of first generation was 0.2, and boom, Excel goes ahead and calculates that for us. And in fact, if you check, this is the same number that we got in class. To do the cumulative probability, so what is the probability that it takes 10 or less trials for us to see our first 5 first generation students? what you would want to do is the same formula. In fact, I might just copy it, paste it. Oh, what'd I do? Oh, goodness. I want to just copy this. It's the same formula. The B4 minus B3. The B3 doesn't change, the B2 doesn't change, but instead of 0 at the end here, I'm going to put a 1 because I want the cumulative probability, which is what this is right there. And we didn't actually calculate this in class, but if you go ahead and write it out yourself, they should be equal. The other thing that we had was I gave you what the expected value and the variance were. So expected value was R. Nope. So I press equal and I take R divided by P. That's the expected value. And then if I wanted the variance, it's going to be equals R. So R times 1 minus P all over P squared. There's variance. Pretty cool, huh? So this is really nice. And if I were you, I would actually snazz it up a little bit. I think it looks a little bit nicer. So these are inputs. These are consequences. So maybe so like you input things that are yellow and you take out things that are blue. And I don't know, I like to color code things a little bit. So maybe I'll do something like this, and boom. Now I have basically a cheat sheet for the negative binomial distribution. If I know my 3 numbers, I can place them in here, and I can get out every single thing we might want to ask about the negative binomial distribution. So now that we've done this with one, let's try doing it with another. So that was the negative binomial. Maybe let's try the Poisson next. So here, I'll do merge and center. I'll say the Poisson distribution. And what are the things that we want to input for the Poisson? We want to have, did I call it K? Yes, so K, which is the number of events that happen in the fixed time interval. We want, I think we called it lambda. That was the name of that Greek symbol, which is the long-term rate. And that was actually it for the Poisson distribution. So these are our 2 things that are inputs. I will make them yellow. And then what do we want as an output? We want to know the probability that a random variable is equal to K, probability that in a day we observe K heart attacks in New York City, right? We might want the cumulative probability as well. So it's the probability that we observe less than or equal to K heart attacks. So if I was interested in 4 heart attacks, what's the probability that I see 4, 3, 2, 1, or 0 heart attacks in a given day? So that's called cumulative probability, right? Then in the same thing, I might want to calculate E of X and variance of X. So how do we do this one? So the probability X to the point, there's also a built-in function in Excel for this. It is poisson.dist. And here for the first input, I want to put in K. It takes in K as the first input. Second input, it takes in the lambda value, the rate. And again, we put 0 for the probability at a point and then 1 for cumulative. So in this case, I'm looking for the probability at X equals K. So I'm going to put 0, right? So don't worry about any of the numbers. I haven't put in any specific numbers yet, but the P of X is less than or equal to K. It's going to be the same thing. Poisson distribution, where the first value is the K, the second value is the lambda. And now I want cumulative, so I'll make my third value 1. And then actually, E of X and lambda of X are both very easy. They are both just lambda, whatever lambda is equal to, right? That was a cool thing about the Poisson distribution, is the mean and the variance are always equal to one another. So let's try to put in the numbers that we got in class. So I think our long-term average was 4.4 in class, and we asked what was the probability of X equaling 4. And yeah, this matches, we calculated this, X equals K in class, and it looks like the probability that we calculated in Excel matches. So once again, I think it's very nice to put in the time to actually make this look nice, so I would do that. Maybe it's just me though. Maybe I'm wasting your time, but I always think it's a lot nicer when you do everything like this. Boom. And there's your cheat sheet for the Poisson distribution. That was Poisson. Let's do the binomial. So, binomial. Cool. So what are the things we have to take in for the binomial distribution? That is the number of successes, right, that we want to see. We have n, the number of trials. We have p, the probability of success. Sounds pretty good to me. And I think those are our 3 inputs. So again, I'll make these yellow so we know you only change things in yellow, you never change things in blue. And then what might I want to know? The probability that I observe k successes in n trials, the probability that I observe k or less successes in n trials. The expected value of x might be interesting, and so might the variance. So what is the probability of x equals k? There is another built-in Excel function to do this for us, which is very nice. You all already did all the work of calculating out these formulas by hand. Now I am literally handing you the way to just do it in Excel and have it done for you instead of having to go through all of that algebra and arithmetic to figure it out yourself. So the first thing you want to put into the binom.dis function is the number of successes, k. The next thing it wants to know is the total number of trials, n. Probability of success is the third thing, and then the fourth value is this, like, is it cumulative, is it not cumulative? So in this case, it's just x equals k, right at a point, so we put 0. Whereas for the next one, it's x is less than or equal to k, so that would be the same thing. We want number of successes, total number of trials, probability, except now that we're doing cumulative, it's going to be 1 at the very end, so that's that. E of x for the binomial distribution is just equal to n times p. Boom. Variance is n times p times 1 minus p. Boom again. So if we wanted to know, if I'm flipping a fair coin, so my probability of heads is 0.5, and I want to know, flip it 10 times, what's the probability that I observe 3 heads? Boom. What you see right here is the probability that you observe 3 heads, 0.11711875. Right here, we have the probability that we observe 3 or less heads. So 3 heads, 2 heads, 1 head, or 0 head. And notice it's greater probability, since instead of just looking at 3, we're looking at a bunch of different numbers and adding them all up, which that checks out. And once again, I'm going to use up your time to make it in the pretty way that I want it to be. Look at them. They all look the same. Isn't it great? I think it's great. There we are. So these are our first 3. The next I wanted to do is the geometric distribution. All right, so the geometric's a little trickier because we're going to have to write out the formula ourselves. There isn't really a built-in formula, or I guess technically there is. Maybe I'll let us use the built-in formula. 1 second. So we need k. We want to know k is the number of trials until success, right? So I'll just say number of trials. And then p is the probability of success, right? So these are the 2 inputs for the geometric, and then the things I want to know are very similar. I might want to know p of x being equal to k. I might want to know that p of x being less than or equal to k. I might want to know e of x and variance of x. Okay. So again, these are our inputs. So the probability of x being equal to a point, it's actually not a difficult formula, so I'm actually just going to type in the formula that I gave you in class, which was 1 minus p to the k minus 1, and I want to take that whole thing, they're all in parentheses, and times it by p again. Okay? So that was that. To get the geometric distribution cumulative probability, there's actually another formula that I'm just going to give you here. I didn't go over it in class, and I'm going to show you why you can decide to use this or not to use this. But if you wanted to know the probability of x is less than or equal to k, there's actually an interesting little trick. It's equal to 1 minus p to the k. Is that right? No, I did that right. I think it's just, it doesn't have any values, so it doesn't know what to do. Oh, not to the k. That's what I did wrong. I put in k and I meant to press k. Yep, I did do that wrong. Okay, cool. So expected value of a geometric is 1 divided by p. Variance is, I believe it's, let's see if I remember this from memory. It's 1 minus p divided by p squared, I believe, right? Boom. Did I do this right? Yeah, I did it right. Okay. Divided by p squared. And it looks like I made the same mistake. Instead of, I wrote in p instead of actually pressing this p itself, which is kind of funny. My bad. You should each refer to whatever value of p that I put in, which is cool. So if I wanted to know what is the probability it takes me 5 trials before I see a success and my probability of success is 0.3, it is all of this. The probability that it takes me 5 trials is 0.72. The probability that it takes me 5 or less trials is 0.83. And this is the expected number of trials and the variance of that trial. So one thing I want to actually note here is that, remember, the geometric distribution is actually the same as the negative binomial distribution when the number of successes we're interested in observing is just 1. So actually, if I go back up to here and I type in, okay, I only want 1 success out of 5 trials, and probability of success is 0.3, you should note, and maybe I should zoom out a bit to see this, that the probabilities here, yeah, the probabilities here are the same. So if I look at these probabilities in blue, the probability of x equals k is equal for the geometric and the negative binomial. The cumulative is equal for the negative binomial and the geometric, and the expected value and variances are also equal. So this is just reiterating the point I made in class, that the negative binomial is a generalization of the geometric distribution. If we set r equal to 1 in the binomial distribution, you're really just doing geometric. So this last, I mean, maybe it was worthwhile to do this last table, but actually, instead of even making this last table, you could just remember that thing about the negative binomial, and whenever a geometric problem comes up, just plug in r equal to 1 for the negative binomial, which is kind of nice. Okay, so that was the geometric. We're almost through all the ones I've gone over. I actually wanted to tell you could do this as well for the normal distribution, which is one that we've been doing a bunch of, right? So I'll write normal distribution. Okay. So what are the inputs for the normal? We have mu, which is the mean, right? We have sigma, which is the standard deviation. What else do we have? I think those are, oh, well, I guess, and then we also have x, which is the value that we want to investigate, right? Yeah, maybe I'll call it k in this case, or I'll call it little x. Okay. So these are our 3 inputs. We'll make these yellow, like these are convention. And what might I want to know? I might want to know the z-score, maybe. I might want to know the probability that x is less than or equal to little x, or I'll do it this way. X is equal to x, sure, we'll keep in cadence what we've done up until now. X is less than or equal to little x. And then expected value of x, sure, and variance of x, sure. Okay, so these are the same things we investigated for everyone else. The things maybe I should start off with is, what's the probability of a point for a continuous distribution? It's just always 0. So maybe you don't want to put that in your table, but if you did, it might also remind you every single time you go in to place stuff in that, hey, it's always going to be 0, no matter what your value of x is. And actually, the expected value and variance are also just about as easy. Expected value is just mu for the normal, easy peasy lemon squeezy. And the variance of x is just the sigma value squared. So that's not hard at all. The more interesting ones are the z-score and the cumulative distribution. So z-score is going to be, it's going to be what? It's going to be our x value minus our mu value divided by our standard deviation value, right? That gives us a z-score. And then the normal cumulative probability is going to be norm.s.dist of our z-score, and then 1 because we want cumulative. Okay? Actually, I might go ahead here. I'll add a row. Here's a little trick. I just remembered something we might actually want to have in this equation is if that is x is less than or equal to little x, what's the probability that x is greater than little x? And that's just going to be 1 minus the probability x is less than or equal to x. So you can do the complement in this table as well. So this is how everything kind of comes in together. Let's make them some numbers. Maybe my mean is 50, I have a standard deviation of 5, and I want to know the probability of being at or below 45. So these are all my values. My z-score, yeah, I'm 1 standard deviation below the mean. Z-score of -1, that checks out. And then the probability of x at a point is always 0, and then I have my cumulative probability, my complement, my mean, and my standard deviation, and my variance. So again, these are all these blue. Ooh, I think it's the wrong shade of blue. It's gonna bother me. Yeah, and there's our table for the normal distribution. And any distribution, you can go ahead and come up with one for the uniform if you would like. You can come up with one with a triangle distribution if you really want to go above and beyond. But these are actually very good things to do, especially when you're practicing for when you're getting ready for your exams, because you can bring this with you on an exam, and you can use it to just quickly get the calculations for these distributions. Which maybe I'll make a few tiny points for you, important points. And that is the difficult thing with problems is figuring out which of these to use. So now that you have these formulae, now that you have these boxes that basically do all your calculations for you, what's really going to be difficult is when you are presented with a problem, you need to determine which of these boxes that you need to use. And that is something that I hope to give us more and more practice on, and so that you'll be well prepared to do this in your actual careers. But no, computers take away a lot of the difficult calculations from us. So what we need to do is figure out which calculations are actually needed. And that's frankly that was the difficult thing to do in the first place. So that makes things easier, but it doesn't make things too much easier. And the other point I want to make about this is it is up to you to make sure your boxes are correct. And I mean this I mean this kind of solemnly, is that you can make these boxes, but if you don't check your results and you put in something wrong here, all your answers are going to be wrong. And that can be hugely detrimental to you whenever you enter an exam, right? Or you're doing your homework and you're placing numbers in here and you're getting wrong answers and you're wondering, did I do something wrong? Whereas really, no, your box is doing something wrong, right? So it is up to you to check these. I really encourage you, after you make these boxes, to write out some stuff by hand, make sure you get the right answer, and make sure your box agrees with your answer, right? Okay, because I'm not going to post this. I think part of the exercise here is for you to make this yourself, right? I'm not going to give you mine. And further, it's important, since you're making it yourself, for you to be accountable that what you've done is correct. All right, so my warning to you is this is a very good thing to do. It'll speed up your calculations. It'll help you manage everything in your head and organize things, but you need to double check yourself. All right, I believe that was everything I wanted to do. I don't think I'm missing any distributions. I guess I also went over the uniform. Maybe at some point I'll post how to do it on the uniform, but I think this is all I want to do for the time being. So thank you, everyone, and I'll see you tomorrow.